So, in this lecture, we basically recap the previous lectures as well as we'll give some of the example of pumping lemma. So, as we know that the type of automata basically we broadly consider that it is a finite automata and push down automata as well as Turing machine. And we have covered the deterministic finite automata as well as non-deterministic finite automata. Push down automata also have deterministic push down automata as well as non-deterministic push down automata. Then there is a classification of different kind of Turing machine also. So now we have covered these portions right now. Now, as we have seen that we can create languages which are basically accepted by the finite automata. So in the last lecture, we have discussed that pumping lemma. So pumping lemma are basically based on the principle of pigeonhole principle, and pumping lemma is basically used to prove certain sets not to be regular. So finite automata, we have also shown that the we have also understand the power of the finite automata. So we also understand that there is a limitation of the finite automata also. So limitation means that we show how to prove certain languages cannot be recognized by a finite automata. For example, so this is one of the limitation of the finite automata, certain sets like suppose we have a language of that form 0 to the power n, 1 to the power n, where n is suppose greater than or equal to 0. So now if we attempt to find a deterministic push down automata, a deterministic finite automata for this language, so we discovered that machine teams need to remember how many zeros have been seen so far from the input, because equal number of zeros followed by equal number of ones. So the pattern of the language is basically it will be epsilon, it will be 0 1, it will be 0 0 1 1, and so this is basically the pattern of the language. So it has to remember how many zeros it has encountered and followed by the same number of one. But that means, but here the problem is the number of zero isn't limited, right? And so the machine will have to keep track of an unlimited number of possibilities. But using the finite automata, or we can also say it cannot do so with any finite number of states. So it is basically the language L is basically not regular. Also, we have shown in the previous lecture that this is not a regular language. So using pumping lemma, we can prove that it is not a regular language. Now we'll show certain for more example of this type. Suppose our question is like that. Um, Language L is given of that form. Suppose a to the power I and b to the power j, where I is not equal to j and is not regular. It is not regular language. Now, what is the meaning of this language? It means uh, a should not be equal, I should not be equal to j. That means same number of a will not follow same number of b. So the possibility is there is a two case occur, right? So case one is I should be greater than j, and case 2 is j should be greater than I. So there is a two possibility of the strings that are basically generated by this. So as we know in pumping lemma, initially we have to assume that L is regular. So we assume L is regular. Now by pumping lemma we can write, so by pumping lemma we can write Z equal to A to the power I, B to the power J. That is U, V, W. In this pattern, we can break this language such that mod of U, V is less than equal to N. N is the number of state of the finite automata, and length of V should be greater than 0. So now for the case 1, for the case 1, we assume that so we have to participate the string or the language in this form U V to the power V of 3 parts we have to participate in this way. So now we assume for the first case that V is of the form A I minus J. Okay. So we assume for the case 1 that V will be this. So we consider V from the A's part. And for case 2, we assume that V is equal to B to the power J minus I. Yeah. So we consider, so as actually here the number of A's should be greater than number of B's followed by number of B's. Like example is like that in this way, A, B, B, and so this will pattern, but this will basically belongs to the case 1, and it will be like that A, B, B, and B will be this. So any number of B's, but should be greater than the number of A's. So these are basically for the case 2. Now we assume for case 1 V equal to A to the power I minus J, and for case 2 V equal to B to the power J minus I. Now for the case 1, uh, so Z is U V to the power K and W, where K is greater than or equal to 0. It should belongs to the language, right? So it belongs to the language U V to the power K belongs to the language for all K greater than or equal to 0. Now we can write that Z is equal to U. U is basically considered in this way. Look, A to the power J, and V is considered, already we have mentioned that V is equal to A to the power I minus J, and W is basically B to the power J. So B to the power J is basically W. So what we have considered here, it is basically U, it is basically V, and it is basically W. So what actually and it is basically K, right? Now for K equal to 0, Z will be A to the power J and B to the power J. That means same number of A followed by same number of B, which is basically contradiction. Hence, and also you can say that it does not belongs to the language L. Clear? So for the case 1, we have seen that it does not belong. So when I is greater than J, so the language, so Z, it does not belongs to this pattern does not belongs to the language L. So also we can say that it is not regular. So not regular. Now what happened for the case 2? Same pattern. So in case 2, what happened? We can write Z is equal to, in the same pattern we can write, here we have considered that U is basically A to the power I, but V is basically B to the power J minus 1, and W is basically B to the power is basically I, B to the power J minus I, and W is basically B to the power J. No, sorry, B to the power I. It will be B to the power I. It will be B to the power I. Right? Now, using pumping lemma, we can say that should be K. So for any number of K that K greater than equal to 0, this should belongs to the language. But what happened for K equal to 0? When K equal to 0, it will be look like this: A to the power I b to the power a. That means same number of a followed by same number of b, which is basically our contradiction. So it does not belong to the language and hence is not regular. Now we'll take another example. Suppose we are given uh, so suppose we are given that L is equal to a to the power p such that p is prime. Okay, is not regular. Is not regular. So simple, we can write that z is in a string of p. Now what will be the length of the string of the z? It will be p, and we assume that it is greater than n. That is length of the string we consider it is a p, and we assume that it is greater than n. It is the number of states. So z can be written as z is equal to u, v and w such that mod of uv is less than or equal to n, and mod length of v is basically greater than 0. Then for all i greater than or equal to 0, u, v, I, w belongs to the language n. Now for proof we assume that let v is equal to a to the power m for some m where m is greater than or equal to 1 and less than equal to n. We assume this. Then this m belongs to 1 to n. So now u v to the power I, length of this can be written as u v w or and length v to the power I minus 1. This is basically length. So u v w plus v to the power I minus 1. So this will basically length. Actually we mean u v to the I w, the length of that string is basically we can write in this way. So it is nothing but UVW is basically we assume that it is a P. So P plus it will be I minus 1 M. It will be this. Why? Because we have assumed that V is equal to as V equal to A to the power M. So length of V is equal to M. Right? Obviously length of V I minus 1 will be m of I minus 1. So now we have obtained that p plus I minus 1 into m. Now we assume that I is equal to p plus 1. So let I is equal to p plus 1. That means next prime number. P is a prime, so p plus 1. P plus 1. I can be any, for all I that should belongs to language. So we consider that I is p plus 1. P is a prime number. Now if we put this value here, p plus I is equal to p plus 1, that is a p of m. Now we take common p as so 1 plus m. Now from this should be prime, but p multiplied by 1 plus m is not a prime. Is not a prime. So we can write that p 1 plus m is not prime. Why? As it has a factor p and 1 plus m, right? So we can say that u v I w does not belongs to language L, and hence L is not regular. So we prove that it is not regular. Now we will take another example. Suppose uh, we have to prove, suppose L, language L equal to a to the power n factorial such that n is greater than 1 is not regular. Regular. So assume initially we let z is equal to any string of this pattern. So what is the length of that string? So length of z will be, it will be n factorial, and we assume that it is n. N means number of state. Then z can be written as u v w such that mod of uv, length of uv together is greater than is less than equal to n, and alone length of v will be greater than 0. Then for all I for all I greater than or equal to 0, u v to the power I w belongs to the language L. This is basically from pumping lemma. Now if we consider, if u is equal to epsilon, then what happened? So then from this we can write length of v is less than equal to n, and here we have considered the length of v alone greater than 0. So we can write, so 0 less than length of v less than or equal to n. So combining these two things, we can write this 0 less than length of v is less than equal to n. Now on both of the side we take that n factorial 0 less than, so u length of u v w or length of v, that should be less than equal to n factorial n, as we have mentioned that z is equal to z equal to u v w. So mod of z is basically mod of u v of length of z is equal to length of u v w. So that's why we have mentioned here, and also we have considered that this length is basically the n factorial. Length of this we have considered that it is a n factorial. That's why we have put here instead of n factorial we just put here length of u v w. So further we can write n factorial less than, it is basically length of u v2 and w, this basically this, that should be less than equal to n factorial or n. Further we can write n factorial is less than of u v2 w and less than equal to n factorial or n, which is again less than n plus 1 factorial. Now what does it mean? It means that after n factorial, it is n plus 1 factorial, where n is the number of n is n can be any number. Now within this factorial, so there is a string of length u v to w, so which is basically a contradiction, because u v to w does not belong to the language L. So because n factorial, if it is 2, then 2 factorial, so it basically 2 factorial, then it will be a 3 factorial. So obviously 2 factorial means 4 and 3 factorial means 3 into 2 means it will be, sorry, it is 2. 2 factorial means it is 2 and 3 factorial means it is a 6. So no string have within this, no string have length within this 2 and 6, because here it is a 4 like 2 and it is uv. So this basically the contradictions. So now we can say that u v2 and w does not belong to a language, hence L is not regular. Now we will give another example. Suppose we have language like this, L is equal to w w, where w belongs to a b star, means any combination of a and b. right? So is not regular, is not regular. So to prove this, let we assume that let W is of the pattern string a to the power n b to the power n, right? Because it is a combination, W belongs to A, B, and star. So one of the string pattern will be a to the power n, b to the power n, same number of A followed by same number of B. So what will be W? It will be a to the power n, b to the power n, and a to the power n, b to the power n. So now Z is any string. So a to the power n, b to the power n, a to the power n, b to the power n. We assume this. So what is the length of that string? It will be 4 of n, and which is greater than n. It is the number of states. Length of this. Now Z can be written as UVW from pumping lemma, or UV less than equal to n and mod of V greater than 0. For all I greater than or equal to 0, UV to the power I W belongs to the language L. So the pattern here is like this. Here the pattern is basically Z. Z is basically of the pattern like this: A, then B, and B, then A, then B, and B. So here same number n. Here B is also the same number, A is also the same number, and B is also the same number. And since UV, length of UV is less than or equal to n, so we choose V from the first set of A, from first set of A's. Here, from here we have to choose. So from here we have to choose the V, right, from the first set, because U and V should be less than or equal to n. Right? So now let V equal to A to the power K, where K is greater than 0. Right? So Z can be written as in this form: A to the power n minus K and A to the power K, then B to the power n, A to the power n, B to the power n. We have taken V from the first set. So what will be the length here? U, sorry, not yes. That means V should be greater than 0. So we have taken from first set of A's V. So now it will be look like this. It is U, this is U, this is V, and this is W. We consider UVW, right? And V as K greater than 0. So length of V obviously K, which is also greater than 0, and UV together less than UV together less than equal to n. So if we take UV together, it will be equal to n from here. So now for all I, UVI should belongs to, for all I greater than or equal to 0, UVI W belongs to the language n. So now the pattern is like that: A n minus K, U V means A to the power K of I, and B to the power n, A to the power n, B to the power n. Now what happened when I equal to 0? It will be A to the power n minus A to the power n minus K, B to the power n, A to the power n, B to the power n, for I is equal to 0. Now as we have mentioned that W equal to A to the power, W is equal to A to the power n, B to the power n. That means if we concatenate both W, then it will be of the form A to the power n, B to the power n, A to the power n, B to the power n. That means same number of A followed by same number of B, again same number of A followed by same number of B. So the pattern here look like this. Here it is A to the power n minus K, B to the power n, A to the power n, B to the power n. But n minus K is not equal to n. Why not? Because K is greater than 0. So if at least k equal to 1, then n minus 1, obviously it is n, is not equal to n. So it will not follow this pattern into same number of a followed by same number of b. So we can say, or we can conclude that this language L is not regular. Now we'll take another example. Suppose L is given W and W R means reversal, where W belongs to A, B star is not regular, is not regular. So again same pattern we have to follow. Let W equal to A to the power n, B to the power n. Then what will be WR? It will be B to the power n, A to the power n, reversal of the string. So what happen if we write WR? It is basically A to the power n, B to the power n, then B to the power n, A to the power n. That means same number of A followed by same number of B, and the second part same number of B followed by same number of A. So now we assume that Z is any string of A to the power n, B to the power n, B to the power n, and A to the power n. So what is length of this string? It will be 4 of n, which is greater than n. N is the number of state. So now for all I, so Z can be partitioned into in this pattern U, V, W, such that mod of U, V less than equal to n and mod of V alone greater than 0. We have to partition Z in such a way that will meet this condition. Now for all I greater than or equal to 0, U, V, I, W belongs to the language L. Right? Now the pattern is of this string is basically it will be like that: A, then B, A, sorry, no, A, B, yeah, B. It will be B, B, again B, and A. That means here n number of A's, n number of B's, and here n number of B's, n number of B's, here also n number of B's, then followed by n number of A's. Now to satisfy this condition that mod of length of UV less than equal to n, we have to choose V from the first set of A's. Right? So now we choose V from the first set of A's. Now choose V from first set of A's. So we can write Z is equal to A to the power n minus k, A to the power k, then B to the power n, and B to the power n, then A to the power n, where we have choose that V equal to A to the power k such that k is greater than 0. So then length of V, which is obviously equal to k, which is greater than 0, condition satisfied, and together UV. So here we have considered that it is U and it is V, and the whole thing is basically W. Now UV, length of UV together, obviously it is n. Obviously it is satisfied this condition equal to n. Now for all I, it will satisfy this condition or using pumping lemma. For all I greater than or equal to 0, U, V, I, W belongs to the language L. So now it will be n minus k, A to the power k I, B to the power n, B to the power n, and A to the power n. Now for I equal to 0, it will be A to the power n minus k, B to the power n, B to the power n, and A to the power n. Now our string that we have considered it same number of A followed by same number of B's, but as k is greater than 0, as k is greater than 0, hence n minus k obviously not equal to n. So L is not regular. Now, okay, thank you. So these are the few examples that we have shown in this lecture.